these are the problem types. These are the two types of problems that we will be testing on next week. They're either going to be one location or two location, and we are very conveniently, because of time constraints, going to have them all where there is no work in or no work done by friction. So they are going to be ME1 equals ME2 problems. Now, with that said, if we look at these equations, that means I'm not going to worry about this form of this equation, and I'm not going to worry about these three equations up here. But in order to determine ME or ME1 equals ME2, we need to make sure we're good with these. Like, is it moving? Is there a height? Is there a compressed spring? So that's what we're going to be doing. A couple people emailed me yesterday about some questions on conservation 2. So if there's a question on conservation 2, there should be some time at the end of class. We are going to deal with PEEs. We're going to deal with springs. So when we deal with springs, one thing to keep in mind is there's certain types of springs that have, there's a certain situation that we can have with springs that are, they're at a point that we refer to as maximum compression. And when a spring is at maximum compression, it is stretched as far as it's gonna be or compressed as far as it's gonna be, and the motion of that object is gonna be 0. Okay, take a big bungee cord, you tie it around your waist, you tie the other end to a tree, and you run as far and as fast as you can that way. Eventually, that rubber band, assuming it doesn't break, your bungee cord, is gonna stop you. So at maximum compression or stretch, doesn't matter, your velocities are 0. So that's like a kind of special problem type. Grab your packet that we've been working through called In-Class Energy. I'm gonna have you try a problem, then we'll walk through it. Then you're gonna try a problem, we're gonna walk through it, okay? So we're gonna start on the last page, it's page 5. And unfortunately it's not numbered, but page 5, and it's the first question listed. How much energy does? And I would encourage you to draw a picture, but how much energy does a 1.2 kilogram block have that is moving at 3 meters per second while compressing a 200 Newton per meter spring? Now, all of your equations are listed. Hopefully you wrote them on the back of this packet, but that's what we're going to be looking at, okay? And I can put them back up there. In-class energy, page 5, the last typed page, the problem on the top that says how much energy. So is it a 1 location or is it a 2 location? Based upon whether it's that, is it moving, is there a height, is there a spring, compressed spring? And that's where we're kind of going to go with those. When we draw our picture, we want to make sure we label our stuff by units. Newtons per meters are indicated for K. How far is my spring stretched or compressed? 0.2. My velocity is 3. My height is 0. So based upon that, it's a 1 location problem. ME is equal to this. Because my H is 0, we could cross off PEG. So then it becomes, all my mechanical energy is from these two forms. If we expand these equations out, we get this. Then we're really just left with plugging numbers in. And once we plug our numbers in, we should get a value for 9.4 joules. Okay, 9.4 joules. Questions on that one? Let's turn back a page to page 4 with emperor penguins. Now we did the emperor penguin on the bottom that had the spring doing the belly slide. We are going to do on page 4 the top problem that has an emperor penguin doing a belly slide at 20 meters per second to the top of a 12 meter tall hill. How far up the second hill, which is 35 meters tall, extra information that's not necessary, how far up the second hill will the penguin make it, and assume that that hill is frictionless. So that is the idea of this next one, 1 location or 2 location, figure that out first. On the picture that's already provided, I would encourage you to draw and label these H's, and if they're spring stuff, to label spring stuff. To give that one a try. All right, let's talk about our picture. because from our picture, then it should kind of make hopefully things easier. So we have a hill and we have a second hill. The fact that this hill is 35 meters tall, who cares? Okay, we just want to figure out how high up that hill they're going to make it. So looking for V's, we're looking for H's, and you could say we're looking for spring stuff. However, is there any mention of spring at all?
No.
No, so we don't care about spring stuff yet. I'm sorry, we don't care about springs in this problem. So at location 1, how fast is the penguin doing a belly slide at the top of this hill initially, at location 1? 20 meters per second. And if from the bottom of the hill to the top of the hill is 12, I'm gonna argue that most people, argues maybe not the right word, I'm gonna make the statement that most people are probably gonna say that my H1 is gonna be 12. And that makes a lot of sense that if we define the lowest point of the hill to be 0, then H1 would be 12. And it makes a lot of sense to make the bottom of the hill 0 because I'm trying to figure out how high up the second hill is. And I could define this as 0, but then my overall height would be, I'd have to add 12 at the end and get kind of not as nice. But if I'm trying to figure out how high up that hill does the penguin make it, how fast is the penguin going to be going at its highest point? 0, right? Because if he's moving up, he's still going to be going further, so that wouldn't be his highest point. But at that point where he is not going to go forward anymore, when he stops, that would be his highest point. Now, unless he puts his feet down, unless he puts his feet down, he's going to slide back down the hill at that point. But that's what we're dealing with. It's a 2-location problem. It's an ME1 is equal to ME2. And I'm going to hit pause on the video. Well, you should hit pause on the video. And you in the class, I'm going to give you a little bit more time to finish up this last bit. So ME1 equals ME2. This equation expands out to be this. And by labeling my V1s and H1s and V2s and H2s, it should make this equation a lot nicer. At location 1, we said there was a V1, so there's a KE1. At location 1, we said there was an H1, so there's a PEG1. There is no spring at either location. At location 2, we said there was a V, we said V2 is equal to 0, so therefore no KE2. At location 2, we said there was an H2, we just don't know what it is, and there's going to be no spring. What this breaks down into is KE is 1/2 MV1 squared, plus PEG is M times G times H1, plus 0, which is equal to 0, plus M times G times H2, plus 0. Algebraically then, we plug in our values and we should get an overall answer of 32.41 meters. The penguin doesn't make it all the way to the top of the 35-meter tall hill, but we don't care. That's not the question. The question is, how high up the hill does the penguin go? The answer is 32.41. Questions that I can answer about that. It's a 2-location problem, but there's no spring involved in this particular. Okay. Last problem that I plan on going through as a class is on page 5 once again, and it's the last problem of the packet. And the last problem on the packet, on page 5, the second question. The question reads, a 4.5 kilogram block was moving downwards, straight down, at some velocity towards a 3,000 Newton per meter spring. That is 3 meters below. How fast was the block moving at location 1 if the spring's maximum compression at location 2 is 0.4 meters? We have an object, it's moving, we don't know how fast it's moving, it's some distance above a spring, and it's going to hit that spring and it's going to compress it to maximum compression. And remember, at maximum compression, we know a velocity number, so keep that in mind. Okay, so I would encourage you to draw a picture first, then label velocities, heights, spring stuff, at each location, and then to solve. Pause your video, set it up. Once you get the picture drawn, unpause it, we'll kind of walk you through that, and then we can kind of look at your picture, see if you kind of have what I have. So based on the information given, mass 4.5, there's a spring. It's 3 meters above the spring, and the block is moving downwards towards that spring. It's going to compress the spring, and it does tell us maximum compression. So it does tell us that that spring is max compression, and that's going to tell us something, and it's actually going to tell us that velocity. So let's just kind of quick go through, where's my question mark? Which one of these variables are we solving for here? Yeah, it's asking how fast was that object moving at location 1. That's my V1. Now, if that's my V1, what's my V2?
Nothing.
Because it's at maximum compression, my V2 is 0, right? It stops. Now, right after that, it's going to start going back up. What do you want to call our H2? Let's start there. Okay, that's fine. If we choose H2 to be 0, and that's probably the most commonly chosen number, that means this right here, this dashed blue line is 0. At location 2, if my H2 is 0, then how far is it from here to here? And a common mistake that people will say is, they'll say, and I'm going to erase this in a second, that this is 3. Well, from here to here is 3, but we're saying how far is it from here, 0 to here, so it's not 3. It's from here to here is 0.4, from here to here is 3, this is 3.4 meters. Now for K2, we are looking for something that tells me newtons per meter, and it tells us that we have a 3,000 Newton per meter spring, that's my K, and my X, 1/2 kx squared, is how far is that spring compressed or stretched, and it looks like that. I do want to point this out really quick, that if you would have chosen this to be 0 meters, this black dashed line, that would have been fine. And if that was the case, then we would have said that H1 was 3. So if H1 from here to here was 3, then that's fine. However, H2 could not be 0, because if this is 0, when this is not at 0, so if we would have chosen this to be 0, that's fine. H1 would have been 3, but that means H2 would have been negative 0.4. Perfectly fine. It's just a different way to define your height to be 0. Typically, the lowest point tends to be our easiest option. I'm gonna ask you, if you're on the video, to pause it to finish the calculation. I'll give you in class a little bit more, and then we'll wrap this up. It's a 2-location problem. ME1 equals ME2. Because ME1 equals ME2, ME1 breaks down to this, ME2 breaks down to this. We ask ourselves the same questions we have for the whole time. For KE, is it moving at location 1? The answer is yeah, I just don't know how fast. At location 1, is there a height? Yeah, I just don't know how fast. Is there a compressed spring? I guess I kind of forgot to mention that. I didn't write any spring stuff here at location 1, because yeah, there's a spring, but this spring isn't doing anything, right? So I don't care about this spring at location 1. That's why I didn't talk about like K1 and X1. Is it moving at location 2? No, maximum spring compression. Is there a height? We defined my height to be 0, but yeah, we do have a compressed spring. We kind of break this steps apart. I'll do that, and I'll let you plug in your numbers. but KE1 is m times v, 1/2 mv1 squared. PEG is m times g times h1 plus 0 equals 0 plus 0 plus, or 1/2 k2 x2 squared. Now, I'll kind of talk about this. The reason I talk about x2 and k2 is because it's the spring at location 2. We could deal with an object that maybe at a location it's the same spring, but it's only like, it's partially compressed. So we call it like K3 or K1 or whatever. It'd be the same K value because it's the same spring, but my X values would be different. We could, and this is not the problem, but we could have a spring that is pushing this thing down, and then this would be a different spring at location 1 than we have at location 2, so that your K1 would be different than your K2, and that's kind of why I talk about K1 in X1. I'm really just talking about what is the spring at location 2 to deal with it that way. From here on out, you go through, you plug in all the numbers that we have already listed, and when we solve for V1, remember this has a V squared, this doesn't. These cannot be mathematically combined. This will have to get subtracted over, and then this has a squared, so you have to take the square root. V1 ends up being 6.33 meters per second. 6.33 meters per second. Questions? Okay, then, what I'm going to do is we still have some time. I'm okay with leaving a little bit early, but not this early. So I'll say right around that 5-minute mark, we can leave. I did come up with another homework sheet, and I really kind of tried to scale back how many problems I put on there. I put 5. Okay, there's 5 problems. Some of them are 1 location problems, some of them are 2 location problems. Some of them have strings, some of them don't have strings. Very cleverly, I called it conservation 3, because these are ME1 equals ME2 problems, and it's the 3rd sheet that's been dealing with that, so very creative, I know. This is the first time I just made this sheet. I haven't actually assigned it, so I fingers crossed the 5 answers that are listed are correct. If you think that I have a mistake, please let me know, and I'll double check and verify, and if I do, I'll send out an announcement to clarify that. But there's 5 problems, and I'm not saying that this is like the test, but these are the type of problems that I'm gonna ask you. I'm gonna ask you about 1 location, how much energies do these things have? I'm gonna ask you 2 location problems, okay? This is the type of questions that will be on your test, okay, for your calculations. Over Friday, like on Friday, my plan is to work on your Socrative to get that posted and ready for you to look through prior to the test on Wednesday. But it's going to be on energy and energy only. There were a couple questions. I had a student email me about conservation 2. If you have questions on that worksheet, now would be a great time to ask. If you have questions on conservation 1, now would be a great time to ask. Otherwise, there's a conservation 3 worksheet that you can be working on, and you have some time, and you want to work with someone. Kitty corner lab table is fine, but I'm also here for any questions too.